Hello everyone. In this video, I have discussed the nature of bonding in metal carbonyl complexes. Various parameters which affect the bonding in metal carbonyl complexes like type of carbonyl ligands, charge on the complex or metal ions, and the nature of pi acid ligands, trans 2 carbonyl ligand are also discussed in detail. I will share all the remaining topics of metal carbonyl complexes in my upcoming videos. If you find my videos helpful, then please like and subscribe to my channel and don't forget to click on the bell icon to get new video updates. Let's get started. We can describe the bonding in metal carbonyl complexes with the help of molecular orbital theory. Before moving to discuss the nature of bonding in metal carbonyl complexes, first understand how the bonding in carbon monoxide takes place. We can plot the molecular orbital diagram of carbon monoxide in two aspects. One is basic, in which overlapping of similar atomic orbitals is described. And if you are in high school or preparing for JEE, then I would recommend you to focus on this diagram only. The other is advanced version, which is plotted based on the conventional AB initio calculation, wherein the overlapping of dissimilar atomic orbitals, that is sp mixing, is shown. And this diagram is useful for third year students and for those who are preparing for JAM, GATE and NET JRF entrance examination. Okay, let us discuss first the basic one, that is without sp mixing. The atomic number of carbon is 6 with 4 valence electron and the atomic number of oxygen is 8 with 6 valence electron. The electronic configuration of carbon is 1s2, 2s2, 2p2. The electronic configuration of oxygen is 1s2, 2s2, 2p4. The potential energy of 1s, 2s, 2p orbitals of carbon and oxygen atoms are shown in the table. Oxygen is more electronegative than carbon, so its orbitals are more stabilized and lower in energy than the carbon orbitals. Thus, the oxygen orbitals have lower potential energy than the analogous carbon orbitals. First of all the 1s orbitals of carbon overlaps with 1s orbital of oxygen to give a bonding molecular orbital denoted as 1 sigma and an antibonding molecular orbital denoted as 2 sigma. Each of the molecular orbitals is occupied with 2 electrons. Now come to the molecular orbitals of valence electron. The 2s atomic orbital of carbon overlaps with the 2s orbital of oxygen to give a bonding molecular orbital denoted as 3 sigma and an antibonding molecular orbital denoted as 5 sigma. These two molecular orbitals are non-bonding orbitals. The 3 sigma molecular orbital is closer in energy to the oxygen atomic orbitals and the 5 sigma molecular orbitals is closer to carbon atomic orbitals. Thus, the bonding molecular orbital 3 sigma is derived from the contribution of 2s2 electrons from oxygen. Similarly, the bonding molecular orbital 5 sigma is derived from the contribution of 2s2 electrons from carbon. Now the overlapping of 2p atomic orbitals of carbon with 2p atomic orbitals of oxygen result in the formation of bonding molecular 4 sigma and 1 pi orbitals along with their corresponding antibonding molecular 6 sigma and 2 pi orbitals. The pi orbital is a doubly degenerate pair that occupies 4 electrons. So, of all 6 electrons from 2p atomic orbitals, carbon and oxygen, 2 are occupied in 4 sigma and 4 are occupied in 1 pi orbital. Both 4 sigma and 1 pi orbitals are closer in energy to the oxygen atomic orbital, while the 6 sigma and 2 pi orbitals are closer in energy to the carbon atomic orbitals. Thus, bonding molecular orbitals 4 sigma and 1 pi are mainly derived from the contribution of 2p4 electron from oxygen. while the antibonding molecular orbitals 6 sigma and 2 pi are mainly derived from the carbon atom. The highest occupied molecular orbital HOMO is 5 sigma, whereas the lowest unoccupied molecular orbital LUMO is 2 pi. Now let us discuss the experimental and the advanced version of molecular orbital of carbon monoxide. From the conventional AB initio calculation, it was found that sp mixing is taking place in carbon monoxide. Because the oxygen 2p atomic orbital is closer in energy to both the carbon 2p and carbon 2s atomic orbitals. These three atomic orbitals will have significant interaction. Because of the mixing of these three atomic orbitals, the potential energy of 5 sigma and 1 pi orbitals increased, while the potential energy of 4 sigma orbital decreased. The energy level of these three molecular orbitals comes closer. As mentioned earlier, the atomic orbitals contribute unequally to each molecular orbital. The rest of the theories remain the same. The 3 sigma and 5 sigma molecular orbitals are derived from the oxygen and carbon respectively. Similarly, the 3 sigma and 1 pi molecular orbitals are mainly derived from the contribution of oxygen, while the 6 sigma and 2 pi molecular orbitals are mainly derived from the contribution of carbon. This is in line with this assumption that electron density is distributed more on oxygen because it is more electronegative than carbon. The conventional AB initio calculation also confirm these hypotheses. The HOMO and LUMO remain the same as mentioned earlier. Okay, let us discuss the nature of bonding between the metal and carbon monoxide. It is clear from the molecular orbital diagram of carbonyl that HOMO and LUMO are 5 sigma and 2 pi respectively, which are weakly antibonding molecular orbitals. Thus, the electron pair present in the 5 sigma molecular orbital being antibonding can easily participate in sigma bonding, whereas vacant 2 pi molecular orbitals are low enough in energy to act as good acceptor orbitals and can participate in pi bonding. Two types of bonding are occurring between metal and carbonyl ligand. First one is metal carbon sigma bond formation. It is formed due to the donation of non-bonding pair of electrons of the carbonyl molecule into the vacant d orbital of metal. The schematic diagram depicted the hat-to-hat sigma overlapping of filled carbonyl orbital with vacant d orbital of metal. The second one is the metal carbon pi bond formation. It is formed due to the back donation of filled orbitals of metal into antibonding orbitals of the carbonyl molecule. This type of bonding is called back bonding or d-pi-pi antibonding overlap. The schematic diagram depicted the sidewise pi overlapping of the filled d orbital of metal with vacant carbonyl orbitals. The metal earlier in the zero oxidation state acquire an excess of negative charge when sigma electrons of the carbon monoxide molecule are donated to the suitable vacant orbital of the metal atom. At the same time, the displacement of electron from the carbonyl molecule to the sigma bond make it positive, thereby increasing the acceptor strength of its pi orbital. To compensate for these effects, the filled non-bonding d orbitals of the metal atom with appropriate symmetry overlap with the vacant 2 pi antibonding molecular orbital of the carbonyl molecule to form a pi bond. The d orbital of the metal atom involved in the back bonding should have proper alignment with the pi antibonding orbitals of the carbonyl molecule. Hence, dxy orbital of metal atom donates an electron to an empty 2px star 2py star antibonding orbitals of the carbonyl molecule. Thus, sigma and pi bond formation reinforce each other. This type of reinforcements is called synergic effect. In metal carbon complexes, the sigma bond formation and pi bond formation, that is sigma donation and pi acceptance, are taking place through the carbon atom only. Evidence of synergic bonding. The energy necessary to stretch a bond is proportional to the force constant. The magnitude of the force constant depends on the bond order or bonding strength. So, the higher the bonding strength, greater will be the stretching frequency. The donation of 5 sigma electron to the vacant orbital of metal led to decrease in electron density in higher energy anti-molecular orbital of carbon monoxide. Consequently, the bond order of carbon-oxygen bond in carbonyl increased as the electrons from the anti-bonding molecular orbital are donated. On the other hand, the acceptance of filled d orbitals electron of metal into 2 pi orbital led to an increase in the electron density in the higher energy anti-molecular orbital of carbon monoxide. Consequently, the bond order of carbon-oxygen bond in carbonyl decrease. Therefore, the stretching frequency of the carbon-oxygen bond increases with sigma donation while decreasing with pi acceptance. On the other hand, the bond order of metal carbon bond increases both in sigma bonding as well as in pi bonding. Consequently, the stretching frequency of the metal carbon bond is also increased. Let us discuss the factor affecting the stretching frequency of carbon-oxygen bond in the carbonyl ligand. The first one is the bonding mode of carbonyl ligand. The stretching frequency of carbonyl molecule consisting of a triple bond is around 2143 cm inverse in their gaseous state. The stretching frequency of terminal carbonyl lie between 1850 and 2120 cm inverse. The stretching frequency of the mu2 carbonyl having two metals directly bonded with a single carbonyl lie between 1750-1850 cm inverse. The stretching frequency of mu3 carbonyl having three metals directly bonded with a single carbonyl lies between 1620-1730 cm inverse. Consequently, we can say the stretching frequency of carbonyl decreases with the number of metals attached to a carbonyl ligand. Since the stretching frequency increases with sigma donation while decreasing with pi acceptance, it is concluded from the experimental data that the tendency of pi acceptance is dominating over the sigma donation, since their overall effect led to a decrease in stretching frequency. Consider the example of hexacarbonyl chromium complex. The complex shows a single band center at 2000 cm inverse in its FTIR spectrum. Based on the value of this peak, we can say that the band is corresponding to a terminal carbonyl. Now consider the example of dicobalt decacarbonyl. This complex shows two bands, one at a higher frequency which correspond to a terminal carbonyl and one at lower frequency which correspond to a bridging carbonyl. The second is charge on the complex. Consider the example shown in this table. Tetracarbonyl iron 2- metal carbonyl has the least stretching frequency and tetracarbonyl nickel has the highest stretching frequency. From the table, we can observe that the variation in stretching frequency of the carbon-oxygen bond must depend only on the charge on the metal, as all the three metals are D10 system and the number of carbonyl ligand is also the same. A negative charge on the metal carbonyl complexes denotes that the metal atom has an excess of electron and can easily donate the electron to carbonyl for back bonding. This results in the strengthening of metal carbon bond and the weakening of carbon oxygen bond. The higher the negative charge on the metal carbonyl, the easier the back donation and the stronger the metal carbon bond. Based on this fact, tetracarbonyl iron 2- being electron rich species can easily back donate electron to the carbonyl ligand. The iron carbon bond is the strongest with maximum bond order, and the carbon-oxygen bond is the weakest among the three metal carbonyls. Tetracarbonyl cobalt -1 has only one negative charge and can also back donate electron, but not as easily as the iron. The carbon cobalt bond is strong, but it is less than the carbon iron bond. In tetracarbonyl nickel, as the metal carbonyl has zero charges, it is an electron deficient species. In spite of being an electron deficient species, its donate electron to form back bonding with the carbon atom of the carbonyl ligand. The nickel carbon bond is the weakest with the minimum bond order, and the carbon oxygen bond is the strongest among the three. This is quite clear from the carbonyl touching frequency. Now consider the following series of complexes of the D6 system, wherein the number of carbonyl ligand is also the same. I have already explained the variation of touching frequency with the negative charges. Now let us discuss with the considering some positive charge complexes. The presence of a positive charge oxidation state denotes that the metal atom is deficient in electrons. Back donating electrons from the electron deficient species is difficult. This is why the searching frequency of carbon oxygen bond in hexacarbonyl nickel manganese plus is higher than the hexacarbonyl chromium. A question may come to your mind: how is it possible for hexacarbonyl iron 2 plus to have carbon oxygen searching band even higher in energy than those in free carbonyl? Actually, this is because of the fact that pi acceptance tendency of carbonyl ligand in this complex is negligible as compared to its sigma donation. So in this complex, the sigma donation tendency dominates over its pi acceptance tendency, which led to an increase in searching frequency of carbon oxygen bond, even higher in energy than those in free carbonyl. Thus, it can be predicted that the frequency of absorption in FAIR will be in the order shown below. The third factor that affects the searching frequency of carbon oxygen bond in the carbonyl ligand is pi acid ligand. Before moving to the effect of pi acid ligands, first understand the definition of pi acid ligands. Ligand which can accept a significant amount of pi electron density from the filled orbital of the metal into its low-lying pi or antibonding pi orbitals are called pi acid or pi acceptor ligands. For example, carbonyl, nitrosyl, isocyanide, phosphine, etc. It is characteristic property of these ligands that they stabilize transition metal in their lower oxidation states. Donor and acceptor properties of other pi acid ligand in transposition relative to each other compete for electron in the metal d orbitals. Therefore, the two carbonyl groups weaken each other bonded to the common central atom. When carbonyl is replaced by ligand which is pi acceptor but weaker than the carbonyl, the metal carbonyl bond in the transposition is strengthened and carbon oxygen bond is weakened. Hexacarbonyl molybdenum complex shows a band at 2008 cm inverse. When 3 carbonyl ligands are replaced by 3 pyridine ligands which are weaker pi acid ligand than carbonyl, the two peaks are observed at 1890 and 1723 cm inverse. Since pyridine is a weaker pi acid ligand than carbonyl, the stretching frequency of carbon oxygen bond are observed at lower wave number. This concept is also confirmed by comparing the frequency of carbonyl stretching vibration for a series of ligand 3 molybdenum 3 carbonyl complexes. Since trichlorophosphine is a stronger pi acid ligand, due to which we observe maximum stretching frequency of carbon oxygen bond in its complex. Similarly, triphenylphosphine is a weaker pi acid ligand, so we observe the minimum stretching frequency of carbon oxygen bond in its complex. Based on the frequency of carbon-oxygen bond, in some complexes, the order of pi acid ligand with decreases in pi acceptor tendency can be proposed. Nitrosyl is the strongest pi acid ligand, even stronger than carbonyl ligand. Both diene and pyridine are weak pi acid ligands. Now I end this video here. Thanks for watching. Please like and subscribe to my channel. See you in the next video of this series.